Hello everyone. So here we are given that group G is abelian and it has the identity element E. Now a set H of which is a subset of G is defined as H is equal to set of all x in G which satisfies the property x square is equal to identity. Okay. Now we are asked to show that this subset H is a subgroup of G. All right. One way is to one way to verify that H is a subgroup is by verifying all the three axioms of the subgroup. Now here let's take a different approach. We will use the one-step subgroup test. Okay. In one-step subgroup test, what does it say? Let G be a group. Okay. What does this say? Let G be a group and let H be any non-empty subset of G. Okay. Then if for all a comma b in H, a b inverse is already in H, then H is a subgroup of G. Now I am going to use this notation less than or equal to for subgroup. Okay, H is a subgroup of G. Okay, so so to use the one-step subgroup test, we have to verify that H is non-empty and that this condition is being satisfied. Okay, there are only two things. All right. Now, once you know this statement, then everything becomes very easy, right? The most of the time took in writing this statement. If you already know the statement, then this applying this one-step subgroup test will take only you a few minutes, right? So here we observe that E square is equal to E, right? So E is definitely there in H, right? So H is definitely non-empty. So this condition is satisfied. Okay. Now let A and B be in H. That means A square is equal to identity and B square is also equal to identity. Now we have to verify that AB inverse is there in H. Okay. So for that, to show AB inverse is in H. Okay, for AB inverse to be in H, what is the condition that it must satisfy? That is to show AB inverse the whole square must be equal to identity, right? Because for an element to be in H, what must it satisfy? Its square must be equal to identity, right? So for AB inverse to be in H, its square, that is AB inverse the whole square, it must be identity, right? So let's compute this. So we have AB inverse the whole square, which is nothing but AB inverse into AB inverse. Okay. Now by associativity, we can write this as A into B inverse AB inverse by associativity, right? Okay. Now we are given that group G is abelian. We have not made use of that fact till now, right? So here it's is it where it comes in the picture. Since it is abelian, we can make further manipulations. Okay, here this I'll just modify this the associativity step. So here what I will do is just to be more precise, let's keep this element as it is. We will write this as A B inverse into A B inverse. Okay, so clubbing these two. Okay, by associativity. All right. Now again, we'll apply associativity to this. So we will have A into B inverse A into B inverse. Okay, again by associativity. So I did not want to jump any step. That's why I'm being pedantic here. But it's understood, right? Yeah. So here first what we did is here we treated this AB inverse as one element, okay, and then we applied associativity. So here it is A B C, so it is AB into C. So here it is in the form A B inverse into C. So I wrote this as this is equal to A into B inverse C by this associativity. Okay, now I applied this associativity inside this bracket. Okay, that's what is happening here. Okay, now given that group G is abelian, so I can commute these two, right? So we'll have this A into A B inverse whole into B inverse by commutativity. Okay, now again I will apply the associativity. So we will have that A into B inverse into B inverse by associativity. Okay. Now we have this actually equal to A into B inverse. Okay, B inverse square, right? B inverse into B inverse. So it's actually B inverse the whole square, right? Now again by associativity, we will have that this is actually A into B inverse square by associativity. So it is actually equal to A square into B inverse the whole square, right? Now we know that A square is actually identity, and B inverse the whole square, this is actually equal to B square the whole inverse, right? This is since A square is equal to identity. Okay, why is A square in identity? We know that A square, we had already brought it here, right? This one. Okay, we are just applying that. Okay, since A and B are in H. Okay. Now we know that and B inverse the whole square is actually equal to B square the whole inverse. Okay. Now again, what is B square? Which is actually again identity, right? Identity inverse, which is actually identity into identity, which is actually just identity. Okay. So what did we have here? We had that AB inverse the whole square is actually identity. That means AB inverse is in H, right? Because the condition for an element to be in H is its square must be identity. Okay, here AB inverse the whole square, it is actually equal to identity. So AB inverse must be in H. Okay, so what did we have here? For any A and B in here, let A comma B in H, these were taken as arbitrary elements, right? They were arbitrary. Okay, so we have that for any A and B in H, AB inverse is in H. So the second condition is satisfied. Hence, by one-step subgroup test, H is a subgroup of